Hello and welcome to today's chat about stellar remnants. I'm going to talk about the uh, eventual end of stars, or sort of zombie stars, if you will. And these are not true stars because there's no more fusion taking place in their cores, but actually the remnants, what's left over after a star meets its demise. So, we're going to talk about all the way from the smallest stars, what they end up to become, to the most massive. In some cases, when a star meets its end, it doesn't leave anything behind at all. So basically, the death of a star can result in a few different objects. The smaller stars, like our sun or like red dwarfs, will produce a white dwarf, which is about the size of the Earth, and we'll talk about that. More massive stars than our sun become neutron stars, which are about the size of Manhattan but have more mass than our entire sun. And then the most exotic objects in the universe, of course, are the black holes, which we have some theories about. We know what the conditions would be to create one, but once inside a black hole, all the laws of physics that we know seem to break down. In any case, let's start with the smaller stars first. White dwarfs, again, are the end product of stars which are very, very low mass. Remember, the red dwarfs can have a lifespan longer than the universe, all the way up to a few times the mass of our sun, probably between 4 and 9 times the mass of our sun would be the upper limit for where we can form these white dwarfs. Again, the neutron star are even more dense remnants than our white dwarf. And these are very, very bizarre objects. They don't contain matter like we know it. They don't contain atoms. In fact, the matter is so compressed that all the protons and electrons in their centers have been basically converted to neutrons, thus the name neutron star. They're incredibly dense. And then finally, again, black holes. These objects are essentially what we call a singularity. At their center, we believe that they have no volume and they have infinite density, which creates an incredibly strong gravitational field. Finally, again, there are some conditions that a star will simply blow itself out of existence, and it will leave behind, you can't say it doesn't leave behind a remnant, it leaves behind a supernova remnant, but it basically takes all of its mass and scatters it back into the universe. Now, starting with the brown dwarfs, we said that brown dwarfs are not really true stars. They don't fuse hydrogen in their cores, so they basically spend their entire life cooling down. So in terms of a brown dwarf, what happens to them? Well, a brown dwarf is just going to get cooler and cooler and cooler. They initially form hot due to the thermal energy that is extracted from the infalling matter. Essentially, we're converting gravitational energy into thermal energy. But because they do have some very small amount of fusion, deuterium fusion and lithium fusion that might take place in them, because this is a very small amount of the matter in the star, it never provides an appreciable amount of energy. So these brown dwarfs just get cooler and cooler and cooler, so theoretically they completely cool down, and they don't give off any thermal energy at all. Now, for this to take place, it would take billions of years for a brown dwarf to cool down. So every brown dwarf that's ever formed is still giving off some thermal energy. But theoretically, if a brown dwarf were to continue to cool indefinitely, it would be essentially a dark body. We would probably call it a black dwarf instead. Now, low mass stars, like red dwarfs, do engage in fusion during a very long period of time. And again, we have to emphasize that no red dwarf has ever become a stellar remnant. That's not entirely true. You can't say never. But for the models that we have, a solitary red dwarf is never going to have enough time in the lifespan of our current universe, the age of the current universe, 13.7 billion years, to have evolved into a. However, we do have pretty accurate stellar models, so we would expect the red dwarf start out with a, essentially mostly hydrogen. As the core became denser and denser, the core would actually increase the production of energy. It would actually cause a red dwarf to maybe get a little bit brighter. But when the core ran out of energy in 100 billion or even a trillion years, strangely enough, losing energy means that it would contract and it would actually heat up. So while it wouldn't be white hot like a traditional white dwarf, it would be, it would be much hotter than an M-class star. So, looking at what a white dwarf would look like if it contracted from, a star about 1/10 of the mass of the Sun, it would probably be much larger than the Earth. Here's the Earth shown here for size comparison. But it also would be much hotter, probably between G and K class when it contracted. Now, here's a strange thing. White dwarfs are made out of degenerate matter. And because they're made out of degenerate matter, as you add more mass, they actually get smaller. Okay? We think of normal matter that we see on the surface of the Earth. And, something with more mass generally occupies more volume. But degenerate matter is just the opposite. So twice the mass of that star is going to be smaller. At about half the mass of the Sun, it would form a white dwarf, which would be just a little bit bigger than the Earth. It would also be hotter. There's more matter. There's more internal energy, so it's going to be hotter. Now, the other interesting thing about this is the white dwarfs that form from red dwarfs, okay, these low-mass stars, the red dwarfs never fuse anything heavier than hydrogen. So all they're ever able to produce in their cores is essentially helium. These white dwarfs would be made out of helium. Okay, they're completely convective, so they'll mix all the hydrogen until all the hydrogen is gone. And again, here's a chart that shows the radius of a white dwarf as a function of its mass. And we see the lower the mass, the bigger the white dwarf. And to be about the size of the Earth, you probably have to be about 80% of the mass of the Sun. It'd have to start out that way. But again, white dwarfs, very similar in size to our own Earth. And again, these red dwarfs, as a core runs out of energy, will contract, will heat up. But after the white dwarf is formed, it will essentially spend the rest of eternity cooling down. And given an infinite amount of time, given trillions of years, it would be completely dark. So again, red dwarfs, they're so long-lived that essentially, no red dwarf has been able to naturally just evolve into a white dwarf when this has happened. The universe is just too old. But again, when the red dwarfs do exhaust all their hydrogen, they will become these helium white dwarfs, and we just say helium because that's the composition. And again, throughout whatever time is left in the universe, if they're left alone, they'll simply keep radiating away energy until finally they become completely dark. So what about the white dwarfs that are formed from Sun-like stars? How different are they from the white dwarfs that form from red dwarfs? Well, the primary difference between the red dwarf becoming a white dwarf and the Sun-like stars becoming a white dwarf is what is left behind is essentially different in composition. Remember, the last phase, the final phase of a Sun-like star is what's called an asymptotic giant branch star, or AGB star. At this point, this star is undergoing helium fusion. It's converting helium into carbon, it's converting helium into oxygen, and helium into a little bit of neon. So, as the thermal pulses located at the center or core of the star blow out the outer lying layers, okay, the outer lying envelope of the star just tears away into space. It exposes the core of the star, and again, the core of the star is all the products of helium fusion. The star started its life on the main sequence, turning hydrogen into helium. It then evolved to become a giant star, and eventually fused, not right away, but eventually fused helium into carbon and oxygen. So now what you have left at the center is this carbon-oxygen core. And what it leaves behind is this very hot core. You know, this is the HR diagram. It's kind of misleading because when the star is a red giant, it's over here. It's going to blow out its outer remnant. So we're left with a core which is much, much hotter than even a blue star. And as it cools down, all the gas surrounding it will glow due to fluorescence. That's our planetary nebula. And then eventually it settles down here to become a white dwarf. So again, what eventually becomes the white dwarf for these stars is the hot core of the star. The hot core of the star heats up the surrounding gas that the red giant is given off during its giant phase. Remember, when it's a red giant, its stellar wind is much more intense. It can shed up to half of its mass, and in doing so, it surrounds itself with all this gas. When the core is exposed, the core heats up this gas and causes it to glow. Now, here's an example or a comparison of the size of our sun, okay, what our sun is like right now, and here's approximately what a white dwarf of the same mass would look like, and that's eventually what our sun is going to become. So they're about the size of the Earth. If you were unfortunate enough to stand on one of these white dwarfs and you could survive the extreme temperatures, you'd probably be crushed to about the thickness of a piece of paper. Again, you've taken something about as massive as our sun, you made it about the size of the Earth. Gravity is much more intense. So everything's under tremendous pressure. Now again, the white dwarfs left over from these types of stars are mainly made out of carbon and oxygen. So the interiors of these objects, not true stars, is all this spent fuel. There is probably a layer of helium, sort of an atmosphere of helium, helium that wasn't able to escape in the outer envelope, and maybe even a little bit of hydrogen. But depending on how the star ends its life, this atmosphere may or may not be present, and may be present in different concentrations. Now again, when we talk about the white dwarf, we can't avoid this term called degenerate matter. We've talked a little bit about degenerate matter and what it is. We've talked about some other objects. But basically, throughout the entire star's life, the star has supported its weight. It's opposed the forces of gravity using the thermal pressure, the heat created in the core. Now that thermal energy is gone. So all the atoms are pushed together at such close quarters that now the electrons are almost asked to overlap with one another. Now the strange thing is, as you confine an electron to a smaller and smaller space, it goes faster and faster and faster. Eventually, the electron can't go any faster because it would exceed the speed of light. At that point, the degenerate matter can no longer support the white dwarf. So basically, temperature on degenerate matter has very little effect. You can heat up the white dwarf, and it really won't change size. The stars are very sensitive to temperature in terms of size. And as far as the electron degenerate matter, which is in these white dwarfs, a teaspoon of matter would be about the same mass as an ocean liner. Now, there are different spectral classifications for these white dwarfs. And really, it has to do with their spectra. What is, sitting in their atmosphere? DA class stars have an outer layer of hydrogen, which is thick enough to support absorption lines. DB have an outer layer of neutral helium, and the hydrogen layer is missing. And DO have outer layers of ionized helium, but the hydrogen is also missing. So we're not quite sure why these different states exist for white dwarfs. It probably has to do with how massive the star was when it died. The common thinking is that the lower mass white stars that form the white dwarfs would make a DA, and the hotter it gets in the core, it'd be more likely to evaporate these outer layers. So the more massive stars would form DB or DO. The DO would probably be for a young white dwarf, and as time went by, it would cool down and you get a DB white dwarf. And then the most rare one would be an exposed carbon-oxygen white dwarf. And, this might be the case where the core formed so hot that all the hydrogen and helium went away, but that's perhaps speculation. We talked a little bit about oxygen, neon, magnesium white dwarfs. And these white dwarfs probably form by stars which were right on the limit. They almost went supernova, because the core was almost heavy enough to diffuse even heavier elements than carbon. But this is probably the stars that are right on the limit to going to a supergiant phase and then exploding. Now, there's a limit to how much mass a white dwarf can have before the degenerate matter can't support the star anymore. Again, no white dwarf can exceed about 1.4 times the mass of our sun. We call this the Chandrasekhar limit. It's named after a very famous astrophysicist whose name also is on Chandra, the X-ray telescope. Now, the problem is, if you're over 1.4 solar masses as a white dwarf, the electrons can no longer support the star. The electrons can't go any faster. They can't go past the speed of light. Because, again, as you squeeze them together closer and closer, they go faster and faster. Well, they've reached the speed limit. If you go beyond the Chandrasekhar limit, the electrons are forced to combine with the protons, and you essentially form a neutron star. Now, the interesting information that we get from white dwarfs when we look at their spectra is we get very broad lines. And again, this isn't unexpected. I already said that if you were standing on the surface of these stars, you'd be crushed to about the thickness of a paper. And any time gas is under a lot of pressure, the absorption lines and the emission lines get very, very broad. We call this pressure broadening. So if you saw the stellar spectrum from a normal star and a white dwarf, you would notice there's something wrong with the white dwarf. Not only is it not very bright, because it's not very big. A star about the size of the Earth wouldn't give off very much light compared to a star the size of our sun. But you'd also notice that the spectral lines were really blurred out. And, of course, this is the effect that we call pressure broadening. Really high pressures at that surface due to high gravity. And again, you can see the difference here. White dwarf spectra compared to a main sequence star spectra. And the giant star and supergiant stars really have thin lines because they have very low gravitational forces near their surface. Let's look at some examples of white dwarfs. 40 Eridani B was the first white dwarf to be discovered. And it's actually part of a triple star system. The A star is a K-class main sequence star. It's a little bit less massive than our sun. The C is a small red dwarf, so it's actually not even as bright as B. And 40 Eridani b was once the most massive star in the system, probably about the same mass as the Sun. But as it was a giant star, it lost nearly half of its mass, and now the A star is the biggest one. Even the brightest star in the sky, Sirius, has its own companion, and Sirius B is a white dwarf. The interesting thing here is Sirius B was once more massive than Sirius A. And again, as Sirius B went through its giant phase, it lost a tremendous amount of mass, and now it's a less massive partner. Procyon, another very bright star in the sky. And what's kind of neat is Sirius is Canis Majoris Alpha. It's the brightest star in Canis Major, the big dog. And Procyon is the brightest star in Canis Minor, the little dog. Now, Procyon A is a star which is more massive than our own Sun, and there are some thoughts that it's on its way to becoming a subgiant. Procyon B is a less massive white dwarf. Now, interestingly, white dwarfs, when they pair with giant stars, can have active mass transfer. More than half the stars out in the universe are thought to be binary or multiple star systems. So it's not unusual that stars will form together. In some cases, they'll form so close together that once one enters a giant phase, it'll dump mass onto the other one. Now, in this picture, we're seeing a red giant, which is sort of toward the end of its life, dumping matter onto a white dwarf. Now, the problem is, as mass is exchanged, you can take this zombie star, if you will, the white dwarf, and actually reactivate it again. Not turn it into a real star, but have it give off nova bursts, and in some rare cases, go supernova. Now let's follow this evolution. Let's say that two stars form close together, a smaller mass star and a bigger mass star. The smaller mass star is on the left. So as we know, as stars evolve, the bigger mass star is going to become a red giant first. The other star is going to take a longer time because with less mass, it burns its fuel much slower. But during the red giant phase, the bigger star is going to dump matter onto the little star, causing it to grow. So the smaller star gains some mass. The bigger star eventually turns into a white dwarf. Well, when the second star becomes a giant, it dumps its matter back onto the white dwarf. But the problem is the white dwarf can't really turn this hydrogen into usable fuel in its core, so it can't turn back on, if you will. So what happens with the white dwarf is the matter makes its way down into the surface of the star. The matter basically spirals down until it reaches a surface. When it makes contact with the surface, it builds on the surface where it can detonate. These detonations we call a nova. The hydrogen taken from the giant star is heated and compressed on the surface of the white dwarf until it reaches a critical mass. And under enough pressure, it undergoes fusion explosively. It's like a small bomb. And although the nova doesn't destroy the white dwarf, it can brighten the star system significantly. And that's why they call it a nova. Nova in Latin means new star. And essentially, these nova would suddenly appear in the sky, and everybody would be like, well, where'd that star come from? There's nothing there before. Now, a very good example of this is Nova Cygni, 1992. And this was an intense nova explosion. You can see the rings left over from the explosion. And the white dwarf that produced this explosion had produced flare-ups in the past, and will probably do so in the future. Here's RS Ophiuchi. It's another example of a red giant white dwarf. They call these cataclysmic variable stars because they suddenly become brighter due to an explosion. And this has been known to flare up in 1898, 1933, 1958, 1967, 1985, and 2006. So they'll build up hydrogen on the surface of the white dwarf. They'll build up enough mass. The hydrogen will explode in this nuclear detonation, and it'll blow the hydrogen away, and the remaining hydrogen away, and the whole process begins over again. Now, in some cases, these cataclysmic binary stars can keep building up matter. Matter is transferred to the white dwarf, gets heavier and heavier and heavier. But remember, there's a weight limit. That white dwarf can't become bigger than 1.4 times the mass of our sun. Otherwise, these electrons will no longer be able to support the matter. And this will cause a real problem. Now, basically, there are many different types of supernova. But the basic types are type 1 and type 2. The type 1 supernovas have no hydrogen in their spectra. They're basically created by stars that have died, which have gotten rid of any hydrogen in their outer atmospheres. Type 2 supernova, these do have hydrogen lines. And as we saw in the other chapter, when a very massive star ends its life, if it's not too massive and it still has hydrogen in its outer atmosphere, it will become a type 2 supernova. So a type 1A supernova is not a massive star at all. It's actually a white dwarf which gets matter from its companion star. However, after each cycle of maybe going nova, it's accumulated more and more and more matter. Because when the hydrogen fuses, it turns into helium. This helium will build up on the star, and even the helium can fuse and make carbon. Well, if the white dwarf is getting heavier and heavier and heavier, eventually it's going to exceed that weight limit, and it's going to blow up. Now, when we reach the critical mass, the carbon and oxygen, which are part of the star, can no longer support the weight. They will fuse into much heavier elements, into elements like iron, nickel, cobalt. And as they do so, the white dwarf becomes a huge thermonuclear bomb. Just like its bigger cousin, it's going to blow up. And as it does so, as it detonates, it's basically going to destroy the white dwarf and nothing will be left. Now again, the thermonuclear action happens very rapidly. The elements fuse in a shock wave that's traveling nearly at the speed of light. And most of the material that's left over is nickel and iron. Again, it's a type 1 supernova because there's no hydrogen in its spectra. And we call it a 1A because it was the first of these class to be categorized. Now, surprisingly, the red giant, which has been feeding the white dwarf, survives. Okay, but nothing is left over from the white dwarf. And again, these are very bright supernova. They're actually very important for measuring distances because they all explode at the same mass. They all detonate at 1.4 times the mass of the sun, so they all detonate with the same amount of matter and the same amount of energy. And here's a typical light curve for one of these supernova. At first, all of the light that we see is from the thermonuclear explosion. Then the products of the nuclear explosion, the nickel 5060Ks, and then the radioactive decay of cobalt 56 provides the remaining material. In the year 1006, a type 1A supernova exploded, and we can still see the hot plasma propagating away from this. This is an image taken from Chandra, and the supernova was actually recorded in ancient Chinese astronomy. In 1572, Tycho observed a supernova, which caused him to question the old Greek view of the universe. And again, this supernova is seen, or the remnant is seen, left over using Chandra. In 1604, sorry for the title, Tycho's assistant Johannes Kepler observed a similar supernova. So basically, a star like our Sun, a medium mass star, is going to go through the giant phase and then leave behind a white dwarf. Okay? This white dwarf, initially might light up a spectacular planetary nebula. That only, happens for a few thousand years. This white dwarf will spend all of its life simply cooling. Now, the one exception to this, and this is a rare exception, is if it's in a binary system where it's close to another star, it can go through like this zombie reincarnation, where the red giant will feed the white dwarf matter. In a very, very rare situation, if the red giant can feed enough matter to the white dwarf before it leaves its giant phase, this white dwarf will explode as basically a type 1a supernova. Now the highest mass stars. These leave a very different object behind. The white dwarf is an electron degenerate remnant about the size of our Earth. The most massive stars tend to leave behind an ultra-dense remnant. Most of them are going to leave behind a neutron star about the size of Manhattan. But in the rare cases, it can leave behind the most exotic object in the universe, a black hole. And in some cases, it can just simply blow up and not leave anything at all. So, as we know, massive stars will start like any other stars. They'll form hydrogen. They'll turn hydrogen into helium in their cores while they're on the main sequence. Okay? Medium mass stars can fuse helium into heavier elements, and the most massive stars can form even heavier elements using the heavier elements on the periodic table. For the most massive stars, they build up iron in the core. And when this iron collapses, when this core collapses nearly at the speed of light, the outer layers explode in a huge supernova explosion. We call it a type 2 supernova. And as they do so, they synthesize very heavy elements. But what is left behind at the very center of these explosions is a neutron star. The star which explodes, and we can see a very nice example of a supernova remnant in the Crab Nebula in the constellation Cancer. And the Crab Nebula, which exploded in the year 1054 AD, the core of the star contracted. It became very dense. Essentially, it was so dense that it was made almost out of neutrons. It's about the size of, again, Manhattan. It's only a few miles across. It's anywhere from about 1.3 times the mass of the Sun to about 2.1 times the mass of the Sun. Now, for the Crab Nebula, what was left behind is a very exotic object. Again, it's a neutron star. But this neutron star not only compressed all the mass, it also compressed the magnetic field. As it contracted, it started spinning faster and faster, like a figure skater skating on one leg and pulling their arms in. They'll spin faster because of conservation of angular momentum. The same thing happens to these neutron stars. The star might be spinning very slowly, but during the contraction, it can spin, making up to 1,000 rotations per second. Now, these pulsars basically are these fast-spinning neutron stars where the magnetic field has trapped particles of radiation and it sweeps throughout space. The interesting thing is, much like our Earth, many times the magnetic field is not lined up with the axis of rotation. The magnetic field might point in one direction, where the axis might point in the other direction. As the pulsar rotates, we get this beam of radio waves and X-rays, which basically sweeps out like a lighthouse. And every time it crosses our path, we see a pulse, and thus the name pulsar. Now, the first pulsar was discovered by Jocelyn Bell Burnell in 1967. She was one of the first astronomers to actually use radio telescopes, and she discovered a radio pulse that at first they thought might be an extraterrestrial signal. But they soon realized that this was one of these rotating dead star remnants, that when the beam was pointing toward us, we'd get a bigger pulse. When the beam was pointing at a 90-degree angle, we'd get a smaller dip in the energy. And then we'd get a weaker pulse for the beam that was not as well aligned. So again, the pulsar, the path of the beam, really, in conjunction with the geometry of how we're aligned with this, determines what we see in terms of these radio pulses. Here, by the way, is what the Crab Nebula looks like in the radio part of the spectrum, and here's what it looks like in the X-ray part of the spectrum. You can almost see, where the axis of this magnetic field, or how this axis of the magnetic field is aligned. Now, just like you can have some exotic objects when you have a white dwarf pairing with another giant star, okay, when you have these binary stars, the white dwarf can take matter from the larger companion. We can get the same thing with these neutron stars. If a neutron star is a companion with a giant or a supergiant star, matter will be transferred from the giant star to the neutron star, but it's almost instantly fused into heavier elements, producing X-rays. Hercules X1 is a very good example of a neutron star orbiting a supergiant star that constantly gives off X-rays from this fusion. And, the term, the reason why it's called Hercules X1 is X meaning X-ray source, and 1 meaning is the first X-ray source identified in the constellation Hercules. Other bizarre combinations include binary pulsars, two pulsars orbiting one another. At one time, these were two supermassive stars orbiting one another, and both, went supernova at some point. And now we have these pulsars orbiting one another. And the interesting thing is, it's actually a test for relativity, that both pulsars are very dense, and by rotating very rapidly, we can get their radio signals, and use these radio signals to determine how they're orbiting. But the strange thing is, as they orbit one another, they give off these gravitational waves, which robs them of energy, and eventually these two pulsars will get closer and closer and closer, and eventually collide. When they do collide, we can get one of the most violent events in the universe called the gamma ray burst, where the two neutron stars will merge together and form a black hole. Now, there are other exotic forms for these neutron stars. There's something called a magnetar. Most neutron stars have very, very intense magnetic fields. But a magnetar, for some reason, has its magnetic field magnified 1,000 times greater than a normal a normal neutron star. And as a result, it undergoes very intense, almost like plate shifts on its surface. The magnetic field produces so much stress on the crust of the neutron star, you get what's sort of analogous to an earthquake. And these are thought to be the source of strange gamma ray sources that we call soft gamma ray repeaters. They're not like the intense gamma ray bursts that we see when very massive stars die. But again, we think that they're the result of some of these magnetars. Now, very, very massive stars, when they die, between 28 times the mass of the Sun, 120 times the mass of the Sun, when the core implodes, instead of stopping as a neutron star, okay? In the massive stars that are less massive than this, when they implode, the core will keep getting tighter and tighter and tighter until finally the neutrons take over, and the degenerate forces from the neutrons, not the electrons like the white dwarfs, but from the neutrons, prevent the neutrons from getting any closer. Stop the compression, then we get the neutron star. But what if the gravity is even greater than the neutron pressure, the neutron degeneracy pressure? Well, in that case, nothing is going to stop the star. The core is going to completely implode and collapse into a black hole. Basically, it'll collapse into a point, and the gravitational forces will be so high that even light cannot escape. When this happens, we get another type of gamma ray burst. The black hole forms at the center. Infalling matter forms an accretion disk, and this produces two bipolar high-energy jets, which results in what we call a Type 1c supernova. Now, if the jets are pointing toward us, we see an intense gamma ray burst. If the jets aren't pointing aligned with us, then what we see instead is a very bright supernova. And again, these are usually called long gamma ray bursts, as opposed to short gamma ray bursts, which are thought to be the merger of neutron stars. Type 1b supernova explosions are thought to be created by the same process as a Type 1c supernova. However, the bipolar jets may not get enough energy to break through the star's surface. In any case, what is left behind is basically a black hole, and these black holes we'll talk about in a little bit. But there's sort of an exception to this rule. Generally, we think that anything more massive than about 26 times the mass of the Sun will result in a black hole. But between 120 and 260 solar masses, and to form a star this big is really, really, really rare. We think that we may instead have the star blow up before this core can even properly implode. In this particular case, before the heavier elements can actually even be created, and the core can get dense enough where it's going to form a neutron star or a black hole, the core gets too hot. It destabilizes. It begins to produce pairs of matter and antimatter. And as it does so, it robs the star of energy. The star simply implodes and blows up as a big thermonuclear bomb. In this particular case, what is left behind is nothing. The core never had time to develop, so nothing is left behind. Of course, if a star is really, really massive, over 260 solar masses, which we don't even think can form anymore, then the star is going to fail through a process called photodissociation. Heavier elements that form will simply just come apart due to the high gamma rays, and this will leave behind a black hole. Now again, what is a black hole? Wow. Well, now this question comes up so many times, and there's really no good way to answer this sometimes. The best way to answer this is just to say that, well, black hole is something that has such high of a density that even light can't escape it. And we call the point where light can't return as the event horizon. Now, there's some controversy as to what is at the center of a black hole. Some theories have a singularity at the center, where all the mass of the star has simply been compressed to a point. Other theories state that the black hole, the matter, has crossed the event horizon, has literally come out of existence. It's no longer part of our universe. other theories state that time slows down so much that the surface of the star that's crossed the event horizon is simply just stopped and is frozen in time. Now again, what's the interior structure? We have no idea. Our theories of physics really aren't equipped to, predict what's inside the black hole. But again, the event horizon is, the spherical surface or spheroidal surface around the black hole where the escape velocity is basically at the speed of light. Basically means that anything crossing the event horizon will never be seen from again. Even light can't escape. Again, there's no answer to what happens to things inside. Now, many black holes, if they're near a source of matter, will form an accretion disk. The black hole itself, you can't see. The black hole itself gives off no light. So if you're standing next to it, and you could survive its gravitational field, or you could cancel out its gravitational field, you wouldn't even know it's there. However, if matter is falling into a black hole, as it falls into the black hole, the matter gets hotter and hotter. The gravitational energy is converted into energy. And the infalling matter, sort of forms like a whirlpool or an accretion disk. And usually the result is that the energy given off by the black hole is seen in these bipolar jets, these jets of energy, which are given off at the axis of rotation. And again, it's one of the most efficient machines that there are. Matter falls into the black hole. Sometimes this matter comes from other stars. There has to be some source of matter, otherwise the black hole is inactive. But as it falls in, the matter gets hotter and hotter. And about 10% of the total mass is converted into pure energy, which is ejected in these high energy jets, which typically give off a lot of X-rays. Now, the more massive the black hole, the larger the event horizon. According to Einstein's theory of general relativity, again, time should come to a stop at the surface. But at these high accelerations, we're not really sure, if even relativity would hold. The strange thing is that relativity predicts that if a black hole is rotating, it'll actually cause the fabric of space to rotate with the black hole. Now again, the event horizon for a rotating black hole will actually be sort of an oblate spheroid, somewhat smushed along the axis. But there's also a region called an ergosphere around a black hole where anything at that point, because time and space are actually moving or rotating with the black hole, the ergosphere would mean that any object at that location would also have to rotate. Just like the neutron star, the magnetic field is highly compressed. Whatever produced the black hole, those magnetic field lines would be preserved but compressed at such a high intensity that it would focus any of these energy beams created by the black hole into very narrow channels. Now, one of the first black holes ever discovered was Cygnus X1. Like Hercules X1, it is a very strong X-ray source. But unlike Hercules X1, which is caused by a neutron star, here we have a black hole orbiting a very massive supergiant. So, stars greater than about 8 solar masses, but less than about 20 solar masses, may end their lives as type 2 supernova. Leave behind a neutron star. Again, these neutron stars are very compact. They're about the size of Manhattan, but they're more massive than our sun. These neutron stars, if you were to step on the surface, you would be smushed to about the size of about an atom. You'd be compressed to about the thickness of an atom. Now, stars more massive than 20 to 30 solar masses would probably end their lives as black holes. They produce very intense explosions called hypernova, just very intense supernova. And if we were to line up with the axis, we'd see a strong burst of gamma rays. Now, stars greater in mass than 120 solar masses would be extremely, 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 extremely rare. Okay? But we do think that we've observed one candidate which did undergo this type of collapse, where the core simply collapsed and blew up, leaving nothing behind. And of course, at the very beginning of our universe, we think that exceptionally massive stars formed. Anything greater than 250 solar masses would leave behind a black hole. Here's sort of a chart showing the progression of different stars. Brown dwarfs would simply just cool off and, eventually become dark. Red dwarfs would become helium white dwarfs. Our own sun would become a white dwarf. More massive, they blow up as a supernova, leave behind a neutron star. More massive than that, leaving behind a black hole. And somewhere in between, these pair-production supernovas might completely destroy a supernova, but the most massive stars in the universe, which again probably don't form anymore, would leave behind a black hole also. Okay, that's it for today. Again, the three basic remnants that are left over from stars include white dwarfs, neutron stars, and black holes.